Okay, in this presentation we are going to look at probability and conditional probability in this instance. So we're looking at a medical diagnosis example, and in this we are going to look at a test. So a test has been developed to diagnose a particular disease. Okay, if the person has the disease, the test has a 95% chance of identifying them as having that disease. Okay, so far so good. So, if the person does not have the disease, the test has a 1% chance of identifying them as having the disease. So, this is an incorrect conclusion. In the first instance, up here, the first line, we have a correct conclusion. This is an incorrect conclusion. Now, we're also told that suppose that 5% of the population actually will have this disease, and suppose that we select a random person from this population. Okay. So, two questions. What is the probability that the test will identify them as having the disease? Okay. Okay. And then the second question is, what is the probability that the person has the disease given that the test identifies them as having the disease? Okay. So, it's essentially the concept of a false positive and a false negative. Okay. So, let's just actually look at this first line here again. So, if a person has the disease, the test has a 95% chance of correctly identifying them. Now, the consequence of that is that there's a 5% chance that they don't identify them as having the disease. So that's also an important piece of information there. Okay, so now if the person does not have the disease, their test has a 1% chance of identifying them as having the disease, but that means that there's a 99% chance of them of identifying them as not having the disease. So just look at the extra pieces of information that were given there. Essentially, just think about the idea of complements. Okay, complement events in both cases, because we're able to sort of deduce the probability of the complement events just on that piece of information. So it's almost like we're given 4 pieces of information rather than 2. Now, suppose that 5% of the population has the disease. Also, that means that 95% do not have it. Okay, so that's actually quite a lot to work on. Now, what is the probability the test will identify them as having the disease, and so on? Yeah, we'll just come to that shortly. So let's sort of just read through what we have to do here. Now, this is a sort of important step when dealing with conditional probability, identifying the states, state each of the events. So this is an important thing to do in your exam question here. Just sort of do this part here. Just make a sort of statement about what you're going to do and what P and D and H and so on means. So let P signify that at the event that a test will give a positive result, P for positive. Let N signify that a test will give a negative result. Let D signify that the person in question has the disease in reality, okay, not whether or not they identify it as such. And let HB signify that the person does not have the disease, in other words, is healthy. Okay. Now, in practice, we don't have to. Well, I'm probably overdoing it there. We probably don't need all of these here really in our question, but it's sort of, this is a good step just to sort of say what P and D and so on mean in the concept and the context of how we are going to answer this question. Don't assume that the examiner will follow what you say immediately. Okay, so you could drop points for not doing stuff like that. Okay. So we're asked to determine the following: the probability of a positive test, the probability of P, and then the probability that they have the disease given that they have tested positive, the probability of D given P. So just a sort of a mathematical expression there of what we're actually asked to do. Okay. Now, I've talked a bit about this before. What pieces of information are we given? Suppose that 5% we're told that 5% of the population has the disease, and we know that D and H are complementary events. So that means that we know that the probability of D is 0.05, and the probability of H that they're healthy, or well, that they don't have the disease, but just for the sake of argument that they don't have this disease, we'll call that H, 0.95. Okay, P and N are also complement events. Okay, so that's good. We know that. We won't. Well, sorry, not that we will know that yet, but what P and N are. But we know that they're complement events. Okay. Now, so people who test positive, we could break that up into two groups. Okay, this is the rationale of what we're doing. So the people who test positive, in both cases, and the ones that do have the disease, and then the ones that do not have the disease. So they are. The first group is P and D and P and H. So the probability of P can be expressed as the combination of those two events. Probability of P and D plus the probability of P and H. Okay? So this is a very important little strategy that we're using here. This part here. The law of total probability. Okay? So just consider we're splitting up our group into two piles, let's say. Okay? Now, so what pieces of information were we given? Let's go over them again. A new test has been developed to diagnose a particular disease. If the person has the test, that means that the test has a 95% chance of identifying them as having the disease. So how will we state that using mathematical notation? Well, that is a conditional probability, okay? If the person has the disease, so that's given D, the test has a 95% chance of identifying them as having the disease, as testing positive. Okay, so probability of P given D equals 0.95. Okay, now remember, given D, this is contingent on them having the disease. Okay, so that's why the D is that side of that bar, and we were told it's 95%. If a person does not have the disease, the test has a 1% chance of identifying them as having the disease. So in this case, we're calling that H. Okay, so given H, sorry, I'm not consistent in H and H because I'm spend half my time in London and half my time in Ireland. Anyway, I digress. So if a person does not have the disease, the test has a 1% chance of identifying them as having the disease. So the probability of P given H equals 0.01. Okay. So given that they don't have the disease, given H, that the probability of a positive test is 0.01. Now, the conditional probability formula is useful here. So this is always useful. So the probability of A given B is a probability of A and B divided by the probability of B. Now you just notice there that what is this side of the bar given B should correspond to the denominator of that fraction. Now we can re-express that mathematically. Okay, that essentially just get an expression in terms of the probability of A and B, and that can be written as the probability of A given B times the probability of B. Okay, so we're going to use that. The probability of P and D is the probability of P given D times the probability of D. Okay, so that's 0.95 times 0.05, and that works out to be 0.0475. And we do the same thing down here. The probability of a positive test and not having disease, P and H, equals the probability of P given H times the probability of H. Okay. Now we're told that it's 5% of them do have the disease, so that means 95% of them don't have this disease, and the probability of a positive test is 0.01. So 0.01 times 0.95, that gives us 0.0095. Okay. So put those two together, and we can calculate the probability of P. That is the probability of P and D plus the probability of P and H, 0.0475 plus the probability of plus the 0.0095. Working that out, it becomes 0.057. That's the answer to question 1. Okay. A little statement there probably helps as well, you know, just a sort of a little sentence there. I sort of skipped past it. Anyway, the second part is, the answer to the first part is 0.057. So what we're asked to do in the second part is calculate the probability of D given P. Now we sort of have all the information that we need. Essentially what we have to do is just use the conditional probability formula again. So the probability of D given P is a probability of P and D, okay, which we know to be 0.0475, and we've worked out the probability of P, that is 0.057, so just divide one by the other and we get 0.8333. And yeah, that's it. So that's the answer to question 2. Okay, so that's it. That's our medical diagnosis example.